Welcome again to the another session for transfer subject. This morning we have started to talk about the convection heat transfer. Actually, whole topic for these 2 day sessions and this chapter actually is about the fundamentals and some definitions related to the convection heat transfer. Up to here, I have introduced you some uh, basics for the convection heat transfer, and I told you that mainly in this chapter we may review some information from fluid dynamics because for convection heat transfer, for sure we need to have a fluid, and the properties of fluid are main importance parameter for the convection heat transfer. We finish our discussion by this morning about velocity boundary layer. Okay, we have velocity boundary layer. I have already introduced you what is boundary layer. We have also thermal boundary layer. You know, when the fluid flow reaches a surface, due to the friction, due to the contact between the fluid and surface, the it will be some changes in the fluid property. First of all, its velocity will change. So we will have velocity boundary layer. Moreover, the temperature of the fluid near the surface also will change. So two things will change for the fluid when it is flowing through or through a surface actually. First of all, velocity of the flow will change. Then also the temperature of the fluid will change due to the heat transfer. If we have heat transfer, heat temperature difference between surface and fluid. Okay. About velocity boundary layer, you know, when imagine we have a fluid flow with a uniform velocity like v, when it approaches to the surface, due to the friction between the surface and fluid flow, we will have a counter, and for the velocity of the fluid, and this uniform velocity will change like this. Near the surface will become zero. Far from the surface, it will be almost same as the velocity which we have at the beginning of the surface, at the edge of the surface. So this region, which the property of the flow is mainly affected by uh, the surface, will be called the velocity boundary layer. The region of the flow above the plate bounded by delta, the distance, where the effects of viscous shearing force, viscous shearing force caused by fluid viscosity are exist. So this is due to the shearing force uh, uh, come from the surface to the fluid. And this delta or boundary layer thickness is typically defined as the distance y from the surface, this when the velocity, until the velocity at that y from the surface become equal to 0.99 v. V is the velocity, the initial velocity. U is the relative velocity of that fluid layer. Okay, so the boundary layer regions I introduced to you, that beyond that boundary layer region, we call that irrotational flow region, which the frictional effects are negligible and the velocity remains constant essentially. So this is two region, this region, this region and this region. This is boundary layer region, and above that is irrotational flow region. But how this wall shear stress, is related to the heat transfer. Shear stress is in here when we have a fluid flowing above the surface due to the friction between the fluid and surface. So the shear stress here is friction force per unit area. This is the shear stress which we have. You can see here we have friction force, this word. So if you remember from other subjects, friction force is related to the property of the surface, which we call that coefficient of friction. Later we will discuss about that, but here I just tell you that that friction force for the liquids or for the gases or for different fluids depends on the temperature of the substance. And also the other property which is affected by the temperature of the fluid is its viscosity. And this viscosity also is effective on the shear stress. And you can see here viscosity, here you can see in this graph viscosity as a function of temperature. By increase of the temperature of the gas, its viscosity will increase. More shear stress will be there. But for liquid is in opposite direction. By increase of the temperature, viscosity of liquid will reduce. And why it is important? Because this tau W is the shear force or wall shear force actually. It will be equal to mu partial of u with respect to y at y equal to 0. It means this means y equal to 0 means on this surface. This is y0 means this. So the shear stress will be on that surface, and its value can be calculated by this equation. U is the relative velocity and U is dynamic viscosity. This dynamic viscosity is a function of temperature. Like this, you can see how the force is important and how it is related to the heat transfer. Moreover, it is important when we are going to have forced convection heat transfer. For forced convection heat transfer, we are going to select a pump, a fan, or something like that to move to increase the velocity or move the fluid. Then we need to know how much should be power of that pump. How we can select that pump based on our information and based on the heat transfer requirement, we need to come and calculate the shear. So you can see here why shear stress is important. Because for forced convection heat transfer, we need to have a pump or a fan. So the shear stress is important to have to select appropriate power for the pump or fan. And based on your knowledge from fluid mechanics, you may know that we have two types of fluids, Newtonian and non-Newtonian fluids. The fluids which follow this equation actually called Newtonian fluids. And some other fluid which does not follow this equation, in other words, the shear stress is not in a linear relationship with the velocity, are called non-Newtonian fluid. Like non-Newtonian fluid like blood, ketchup, gravy, mud, and cornstarch especially are non-Newtonian fluid, and they are not covered in our text. All of our calculation will be only for Newtonian fluids. Here in this table also you can see the dynamic viscosity of some of the fluid and 1 atmosphere and 20 degrees Celsius. And see here that viscosity for oil, the glycerin, and in lower temperature especially is higher And then the gases, for example, you can see here the dynamic viscosity, very small compared to the engine oil or compared to the glycerin at negative 20 degrees. So you can see here how much the dynamic viscosity for different substances is different, and it will be effective on the shear stress, and it will be then a parameter for us to decide about the pump, the fan we select. For example, if the liquid is water, for example, it is much bigger than air. So we need more powerful fan or a more powerful actually pump for the water compared to the air due to the higher dynamic viscosity of the water compared to the air. Based on that dynamic viscosity, we can also calculate kinematic viscosity, or no will be equal to mu divided by dynamic viscosity. This is density. So why this is important? Again, here is mentioned. The viscosity of a fluid is a measure of its resistance to deformation, and it is a strong function of temperature. The relationship between the information which I told you and heat transfer. While shear stress also can be calculated by this equation, or tau W equal to Cf rho V power 2 divided by 2. Cf here is friction coefficient. Rho is density, V is velocity of the fluid, and by this also we can calculate the wall shear stress. And friction force over the entire surface is this much. Very important value or force when we are going to select the path. This is F sub F is friction force, and it will be equal to Cf As rho V power 2 divided by 2 As is the surface of which the fluid is flowing about. The friction coefficient is an important parameter in heat transfer studies since, now this is what I told you, it is directly related to the heat transfer equation, heat transfer coefficient, and the power requirement of the pump or fan. Later you will see. In other words, to calculate this friction force, we may need to calculate the H, the transfer coefficient. So that was about the velocity boundary layer. How about thermal boundary layer? Similar to what we had for the velocity boundary layer, when the fluid reaches to a surface and we have temperature difference between the fluid and the surface, then like velocity, if we have a uniform temperature for the fluid, when it approaches the edge of that plate, after the movement of the fluid on the surface, the temperature of the layers of the fluid will be different. Near the surface, almost temperature, and close with the surface temperature of the fluid is almost same as the temperature of the surface. Now, far from the surface, temperature will be same as the uniform temperature which we had before. And this layer or delta sub T is called the thermal boundary layer. So a thermal boundary layer develops when a fluid at a specified temperature flows over a surface at different temperatures. What I told you. Thermal boundary layer, the flow region or the surface in which the temperature variation similar to the velocity. If the temperature is affected significantly by the surface temperature, then we call that, in that region will be called thermal boundary layer. The thickness of this thermal boundary layer, or delta T, at any location along the surface is defined as the distance from surface at which the temperature difference, T minus Ts, equal to 0.99 T infinity minus Ts. So if you remember, for the velocity, it was 99 V. That was the, the thickness of the boundary layer, velocity boundary layer. Here, for the temperature boundary layer, to determine this delta T, we need to find a layer which its temperature T minus Ts is the temperature of the surface. T is temperature of that specific layer. If this T minus Ts is equal to this, then we can say that is the boundary, that is this line, actually, which we can calculate delta T, and we can say that is the distance, the thickness of the boundary. And as you can see here, as much as this flow is, you know, goes further, more distance from the edge, the thermal boundary layer thickness will be higher. The thermal boundary layer increase in the flow direction, like you can see here. Delta T here is bigger than here. Delta T is a function of x. Since the effect of heat transfer is become larger at greater distance from the surface to the downstream as shown. As you can see, this delta T is bigger than this delta T due to this. More heat is transferred to the edge. Up to here you have seen we have velocity. The velocity of the fluid when it is flowing through the surface or above the surface will change, and its temperature also will change. But which one will change faster? You know, the boundary layer which you have seen shows the velocity of the fluid will change by x, but the rate of which one is higher. I mean, heat will be transferred faster from the surface to the fluid, or the velocity of the fluid will be affected faster by the surface. So if the velocity uh, is changing, the change in the velocity is lower than the rate of the change in the heat transfer or thermal boundary layer, then it means the heat convection heat transfer rate is higher. Okay, this is simplified or defined by a number which we call that Prandtl number. Prandtl number, the relative thickness of velocity and thermal boundary layers, which I have already introduced to you, is described by a dimensionless parameter, which we call that Prandtl number. So simply Prandtl number is delta divided by delta T, or this is PR. If you want to show this delta to delta T, like this. And you have seen in previous slide how we can calculate that. In other words, delta means molecular diffusivity of the momentum. How momentum is distributed between molecules. How this velocity is, how much is the rate of the transferring the velocity from molecule to another molecule in the fluid. And how this delta T is molecular diffusivity of heat. How heat or thermal energy is transferred from one molecule to the other molecule. How is the speed or rate of it? In other words, force is transferred faster or heat is transferred faster. Based on this, we can define this Prandtl number. If we substitute the value for these two, we can define it like this. No divided by alpha. No here, you know what is it? It is kinematic viscosity. What is alpha? We call alpha thermal diffusivity. It's a property for the fluid. So by this, we can calculate Prandtl number. And also, if we substitute delta and delta T in this equation, we can have this equation mu Cp divided by K. K is dynamic viscosity, Cp is the specific heat uh, of the fluid, and K is thermal conductivity of the fluid. So we can use this equation for Prandtl number of the different fluids. So in this table, table 6.2, you can see typical range of Prandtl numbers for common fluid. So Prandtl number is the property for the fluid. Different fluid you can see here, like liquid metals or melted, metal, for example, or the gases, water, light organic fluids, oils, and grease. You can see here, Prandtl number for the liquid metal is lower lower than gases. Gases is lower than water. Water is lower than light organic fluid, and vice versa. You can see here, as much as viscosity, here it is not only dependent on the viscosity, it's dependent also to the thermal conductivity of the fluid. As you may know, the thermal conductivity of liquid metal is much higher than gases. If we have same thermal conductivity for them, then it means the heat transfer will be much higher to the liquid. This is also mentioned here. The Prandtl numbers of gases are about 2, 1, which indicates that the momentum and heat dissipate through gas at the same rate. So the velocity and temperature of the gases will change almost same. But heat diffuses very quickly in liquid metals. The transfer in them is higher, and very slow in oils. Consequently, the thermal boundary layer is much thicker for liquid metals and much thinner for oil relative to the velocity boundary layer. This will determine how much time we need to have a effective heat transfer from surface to that side. For example, if it is metal liquid, just in few moments, the heat will transfer from the surface to that fluid, that liquid metal. But if it is gas, we need more time. So we need more volume of that gas as well. So this is the difference. So Prandtl number is an effective and important parameter to determine how is the heat transfer from surface to the liquid. The next topic is about the different regime in the fluid flow. Actually, I already told you we have laminar or turbulent flow. You know about them in fluid mechanics. I showed you how is the different layers in the fluid flow for each one of these regimes actually, and not only for the fourth flow, actually for natural flow, as you can see here also we have laminar flow, you see turbulent, and here we call that transition. To determine, this region, if it is laminar or transitional or turbulent flow, we need to calculate a new value or Reynolds number. You may know about that from fluid dynamics. The transition from laminar to turbulent flow depends on the geometry, surface roughness, flow velocity, surface temperature, and type of fluid. You can see it is too complicated to understand when our laminar flow will become turbulent flow. You can see too many parameters are affected. And it is difficult to determine when the laminar will become turbulent. But all of these, properties are combined and showed by Reynolds number. The flow regime depends mainly on the ratio of the inertial forces to the viscous forces. Inertial forces can be shown by this actually. This is simplified value, not the actual value of inertial forces. And we are not going to go to all of the detail of the calculation, just going to show important ones. So here is the average velocity of the flow, and D is the actually the diameter of the flow. We can say like that. And B, no, actually here is viscous force. This equation can be rewritten like this: rho V average D divided by mu distance, mu and rho density. This is dynamic viscosity. So this is the equation to calculate Reynolds number. The Reynolds number will determine if the fluid flow is laminar or turbulent or even in transition. Later we will see. We have really, a specific values for Reynolds number. Higher than that will be turbulent. Lower than that will be laminar or even transitional and something. So now we have two dimensionless parameters, Reynolds and Prandtl numbers, which can be used to characterize the fluid flow and fluid thermal properties. And we will use these two numbers. You can see they are simple equations. Their value are most often for Prandtl number especially. We need to use that table. So it is much easier to know to compare when you need to consider all of these parameters in your calculation. Based on those information, let's go and and solve the convection equation for a flat. The detail of development of this equation, similar to what we had for conduction. If you remember differential equation for conduction, we need to go to that differential to find those differential. Then we can use boundary condition to find the uh, the constant in that equation. But here we are not going to do that, and we just show them the differential equation for continuity, momentum, and energy for a plate like this when fluid is flowing above that with initial temperature T infinity and B. The coordinate system we select is like this. This is continuity. U is the relative velocity. Rho here is the kinematic viscosity. X and Y are the direction or distance from the reference. Alpha is the thermal diffusivity, is the temperature. So continuity equation, momentum equation, and energy equation or energy balance are for this fluid flow. If we go to the boundary condition, which we have, and write the boundary condition for all of these equations, at x equal to 0 means on y line actually, the velocity is the velocity is v, and the temperature is T on this at the edge of this plate. At y equal to 0, it means on this surface, okay, this is y equal to 0. The velocity is equal to 0, as you know, the stick between the fluid and surface. The kinematic viscosity also is 0, and T for temperature on this surface for the fluid will be also same as the temperature of the surface. At y approaching to infinity, enough far from the surface, the relative velocity will be almost that uniform velocity which we had, and temperature will be equal to the T infinity, the uniform temperature which we have for the fluid. So we can find this from those boundary conditions. If we use this, boundary condition and this equation which we have here, differential equation which we have here, we can find this equation. As I said before, we are not going to the detail of how to find this equation. So velocity boundary layer thickness now based on this differential equation, and boundary layers can be found by delta equal to 4.91 divided by V divided by X. Or if we use Reynolds number, it will be much easier, like 4.91x divided by Reynolds number or local Reynolds number at that specific x. Shear stress on the wall can be also calculated by this equation, tau W. Density, dynamic viscosity, velocity, is the distance from the reference. Or we can use Reynolds. Local friction coefficient or CF. CF is friction coefficient. X means local. For each x actually is equal to tau W based on the shear stress on the wall divided by rho v power 2 divided by 2. If we substitute tau W from here in this equation, we can find the local friction coefficient based on only Reynolds. So if we have local Reynolds number, simply we can calculate the local friction coefficient. And the energy related equation about the temperature and so on can be like this. The temperature gradient on the surface. Now here the partial of temperature with respect to y at y equal to 0 means on the surface will be like this. This is temperature gradient. Maybe in the question you need to calculate. Depends on the T infinity, Ts, V, no, and X, and Prandtl. Local heat transfer equation or coefficient, Hx, very important parameter. Simply if we divide these, if you remember before this, we had that Q dot by conduction equal to Q dot by convection. This comes from that. So Hx is equal to this divided, this is that Q dot by convection divided by the this term Ts minus T infinity. So if we use this, we can calculate Hx using velocity, kinematic viscosity X, and thermal conduction Prandtl number of the fluid. The other thing which we can calculate by this equation is local Nusselt number, or mu x, which will be equal to Hx times x. If you remember, this was L, but here because it is local, we need to use x divided by K, or thermal conductivity of the fluid. If we restructure this and instead of Hx we substitute this, finally we will reach this. You can see here, Nusselt number can be calculated only by this information, Prandtl number and Reynolds number. And Prandtl number and Reynolds number usually are given, they need to be measured experimentally. So this equation is valid when Prandtl number is higher than 0.6. You need to notice this. And thermal boundary layer thickness, or delta T, can be calculated by delta, or the velocity thickness, velocity boundary layer thickness, divided by Prandtl number power 1/3. Or if we substitute delta value in this equation, will be like, so you can see this equation to calculate the energy related parameters. And by using analogy between momentum and heat transfer, or we call that Reynolds analogy as well, we can find interesting properties. For example, here, if you notice, Cfx, or the local coefficient factor, or coefficient, friction coefficient, is related to the local Nusselt number. So friction is a property of the surface and the fluid, but here it is related to Nusselt number. Nusselt number is a value related mainly to the energy. So like this, if you have energy, you can find the force, you can find the friction. And if you have the friction information, Reynolds number, you can find Nusselt number, and then you can find other property for the heat transfer. Later we will see in the example. And also this Cfx divided by 2 is equal to this, which we call that a Stanton number. This Stanton number itself can be calculated by this equation. The local Stanton number is equal to H divided by rho CPV. And if you notice here, we have this additional term, which is specific heat of the fluid, which is a property of the fluid, actually. Or a Stanton number is equal to Nusselt number divided by Reynolds number at the end or at the end of the plate multiplied by PR or Prandtl number. So Stanton, Nusselt, Prandtl, and Reynolds number. You can see some values and numbers which are mainly experimental or from the table. If the Stanton number is dimensionless, similar to Nusselt, Reynolds, and Prandtl, that measure the ratio of heat transfer into a fluid to the thermal capacity of the fluid. It is used to characterize heat transfer in convection flows. Later in next chapters, you will see more about this Stanton number. And the friction coefficient also can be calculated by Nusselt number for flat plate. This is important. Cfx is equal to 0.664 Reynolds number, or local Reynolds number power negative 1 second. Or using this equation, you can calculate local Nusselt number. All of these equations are useful, and we will see in the exam. And modify Reynolds the analogy as well. We will give us this, which is the relation between Cfx, Reynolds number at the end of the plate, local Nusselt number, and Prandtl. Or using the Stanton number, then we can write the relationship between the friction coefficient, local friction coefficient, and the Stanton and Prandtl number. You need to notice that these equations, are valid when Reynolds number is less than 5 times 10 power 5 for flat plate and constant temperature. You need to be careful when you are using this equation. Experimentally, it will show that these relationships is also valid for turbulent flow. When Reynolds number is less than this value, we have laminar. This is our criteria. You may know that from thermodynamics. It is also valid for turbulent flow over a flat plate at constant temperature and turbulent flow inside the pipe. So approximately, we can use these equations for this condition, but cannot be used for laminar flow in pipe. This is information you need to consider when you are going to use this equation. Finally, based on this information, we can write a general equation based on the Nusselt number, friction coefficient, Reynolds number, and Prandtl number for all the conditions which we have, which it depends on the geometry, depends on the Reynolds number and Prandtl number, the value of them, which how much should be M or N. Later you will see we have table for that. If the geometry is, for example, a circle, if the Prandtl number is in this range or Reynolds number is in this range, then how much should be M, how much should be N. In next chapter, we will see more about that. So M and M also are a number between 0 and 1. This is a general equation which we will use later in our exam. Okay, let's see a few examples based on what I told you. The first example here is about a simple example about convection heat transfer. The convection heat transfer coefficient for a closed person standing in moving air is expressed as this. Here we have convection. Why? Because this person is exposed by moving air. So have fluid in motion around this body of this person. Then we have H. We have a relation for that. You can see here, H is a function of the velocity of the air. And this function actually is valid when the velocity of the air is between 0.15 and 1.5 meter per second. And V is the velocity of the air. For a reason with the body, with the person with the body surface area 1.7 meters square and an average temperature and average surface temperature of 29 degrees Celsius, we need to determine the rate of heat loss from the person in windy air at 10 degrees Celsius. T infinity, 10 degrees Celsius. V infinity is given as well. Ts or surface temperature of this body, this person is 29 degrees Celsius. The whole AS also is given 1.7 meters. Now we need to calculate the rate of heat transfer from this body to the surrounding by convection at different velocity of the air. 0.5 meter per second, 1 meter per second, and 1.5 meter per second. First of all, as you can see here, these three are almost in this range. Then we can use this H to calculate, use this equation to calculate H. You know, the convection heat transfer we have here, then simply we can use this equation. Q dot is equal to H AS TS minus T infinity. T infinity is 10 degrees Celsius. Ts or temperature of the body of the person or the surface is 29 degrees Celsius. AS is 1.7 meters squared is given, and H. But H here for part A, B, and C will be different. Why? Because the velocity is different. H is equal to 14.8 V power 0.53. See, given in the question. And if we substitute this, no velocity, this is wrong. If we substitute this velocity in this equation, we can calculate H. And after we have calculated this H, we can simply substitute here and find Q dot for this velocity. For part B and C, you know, this equation is saying all of these information are same, nothing changed for them. Only H will be different for different velocity. Again, for part B, we this time is 1 meter per second. So we substitute that. In part C, again, we have 1.5 meter per second as a velocity for this H. If we substitute, we can calculate H. You can see only H is different, 9 point something, 14 point something, 19 point almost 6. So you can see here higher velocity for the fluid cause higher uh, coefficient for heat transfer, and it will cause also higher, you know, heat transfer rate, 296, 478, 632. The velocity is increased, H is increased, it means Q dot will increase. The other example is related to a cooling of different fruits in the, you know, in the storage and so on. During air cooling of oranges, grapefruit, and tangerines, the heat transfer coefficient for combined convection, radiation, and evaporation for air velocity between these value is determined experimentally. So this H actually is determined experimentally for this range of the velocity of the air, where the diameter d is the characteristic length. If you remember, you know, for Nusselt number, we need to have these characteristic length. Oranges, now here our question is about the orange. Oranges are cooled by refrigerated air at 5 degrees Celsius and what atmosphere at a velocity of 0.5 meter per second. Now we need to determine the initial rate of heat transfer from a 7 centimeter diameter of orange, initially at 15 degrees Celsius, with a thermal conductivity of 0.50 watt per meter degree Celsius. In part B, we need to calculate the value of the initial temperature gradient inside the orange at the surface. at the surface of the orange. We will see why it is important. And finally, we need to calculate the value of Nusselt number here for this heat transfer equation. You can see an illustration and installation of this problem. Arrange the flow, which is air, its temperature is 5 degrees Celsius, and its pressure is 1 atmosphere. Why is the information important? You will see. To solve this problem, first we need to have appropriate assumptions. This is important. First, a steady operating condition exists based on the question. You can have this because there is no hint about the change within the problem with time. Orange is spherical in shape. This is important when we are going to calculate AS, the surface of the orange. Convection heat transfer coefficient is constant, H. In real world, it is not constant, but we can assume because the change is very small. Property of water also is used for orange. So we assume, here whole orange is has properties same as the water. This is also important. So to find the answer for part A, actually, we need to have, to find this Q dot, actually, we need to have some information like H, A, S, T, S infinity. T, S, T infinity we have. AS we can calculate like this, AS equal to pi D power 2. We have a sphere. We have D or diameter. If we substitute, we can calculate AS. How about H? To calculate H, we had this equation. Let's go back. This equation is given here. H is equal to 5.05 K of air or thermal conductivity of air times Reynolds number power 1/3 divided by D. So to calculate H, we need to use this equation. So to use this equation, we need to, how much is K of the air, how much is Reynolds number, and also the D actually. First, let's calculate Reynolds number. Reynolds number is equal to V infinity, or the velocity of uniform velocity of the fluid flow or air, which is 0.5 meter per second. D is the diameter of our object, and no is the kinematic viscosity. We have V, we have D. How about this no or kinematic viscosity? To find this, because here we have a fluid. At the end of our textbook, we have tables which you can find properties for different substances. Table A15 will show you or provide the information about the properties of air at 1 atmosphere pressure. Here also is mentioned that the pressure is 1 atmosphere. So we can use this table. To find kinematic viscosity, we can come to this table. The temperature which is mentioned for the air is 10 degrees Celsius. Then you can see all of other properties, here for. Okay, this is kinematic viscosity, 1.42. Okay, so we can find kinematic viscosity in this table. By this, we can find Reynolds number, which will be, it is dimensionless, which will be 2,454. This is Reynolds number. It is less than that value, that critical value, which I told you, 5 times 10 power 5. If you remember, we had this criteria, And we can use the equation which we have developed. One of them is this Reynolds number, which is already being used actually. Then we have Reynolds number here. Here, how about the K? Also, K is provided. Here thermal conductivity is provided. So K also from the table. Reynolds number we have calculated here. D also is given. Then we can calculate H, or the coefficient, heat transfer coefficient. Now we have H as well. If we substitute this H in our equation for Q dot or rate of convection heat transfer, we can calculate the Q dot or rate of heat transfer for this orange in this cooling process. In part B, we need to determine the temperature gradient at the orange surface. If you remember, for the flat plate, for orange is same, at the surface, we have that stick between the fluid and surface. So the convection will be conduction actually here. Same the way. We have this equation, if you remember, when we are calculating the heat transfer on the surface of the orange. If we substitute Q dot by convection, then if we rearrange this equation, actually this part, then this partial of temperature with respect to R will become this HTS minus T infinity divided by K. We have it, we have calculated already, we have TS, we have T infinity, 15, 5, and K from the table. Then, K, this K actually, because if you notice here, K is for the uh, substance, for the orange. So K here is for the water at that temperature, 0.5 watt per meter degree Celsius. This K is for water because we assume that orange is water. So this is temperature gradient will be equal to negative 475 degrees Celsius per meter. In part C of the question, we need to calculate the Nusselt number. Simply, Nusselt number, if you remember, is equal to H. This is LC, or characteristic length, divided by K. H we have calculated. This K is for air this time. HD is, it was mentioned, characteristic length, 0.07 meters divided by K of the 8 at 10 degrees Celsius. Then we can calculate Nusselt number, which is equal to 68.11 dimensionless. So this is answer for part C of this question. Okay, the next example is about a flat plate. A 4 meter by 4 meter flat plate maintained at a constant temperature of 80 degrees Celsius. So the temperature of that flat plate is 80 degrees Celsius. It is subjected to parallel flow. It means on both sides of this plate, our plate is like this. Then we have flow from both sides. The fluid is air, its pressure is 1 atmosphere, its temperature is 20 degrees Celsius, and its velocity is 10 meters per second. The total drag force acting on the upper surface of the plate is measured to be 2.4 newtons. Very interesting problem. We will see how we can use that analogy. Using momentum heat transfer analogy, determine the average convection heat transfer coefficient and the rate of heat transfer between the upper surface and the plate and air. So we need to determine these two. Start again with the assumption a steady operating condition exists. The edge effects are negligible. Why it is negligible? Because it will change the heat transfer property. When we have a flow, the flow like this, the edge also is affected. But we can assume, because the thickness is small, so we can assume the effect of the edge heat transfer is, or on the force actually, is negligible. The property for air, which we have here, 20 degrees Celsius, 1 atmosphere, again, refer to this table A15. You can find information for the air with those properties. The property like density, property like CP, or specificity, and also Prandtl number, which you can find for air at this temperature from table A15. You will see why these properties are important. We are going to calculate Q dot, so we need to have H, AS, TS infinity. TS, T infinity are given, but AS we need to calculate here. AS Both sides of this plate are in heat transfer process. So to calculate the surface, it will be a square. It will be a rectangular actually. So the thickness, the width times length will give us the surface area for this surface, and we need to multiply by 2 because we have two surface for heat transfer. Dimensions are given, then totally the AS will be 32 meter squared. Okay, so we have AS as. How about H? Let's go to the information which is given. The drag force equation, if you remember, we had this equation for that, or friction force, you can call that, is equal to Cf As rho V power 2 divided by 2. V is the velocity given, density of the air we have already that from the table. As we have calculated here. How about, here, what is, FF even the friction force or drag force also is given. So what we can find by this equation is Cf. You will see why it is important. Cf can be calculated. If you restructure this equation, you can calculate Cf. We have this drag force 2.4, we have rho, we have As, we have V, and we can calculate the friction coefficient. Now, if we have friction coefficient, again, if you remember, we had this equation to calculate H. If you remember, I told you to calculate Q dot, we need to have H. So this H can be calculated by this equation. Cf divided by 2, rho V, dP divided by Prandtl number, power 2/3. We have all of this information, Prandtl number. If we substitute, we can calculate H. So this is the coefficient for heat transfer. If we substitute in this H in the general equation for convection heat transfer, we have As, we have Ts, we have T infinity, H we have calculated here. Finally, the Q dot or rate of heat transfer will be equal to 89,356 watts. You can see how that drag force is useful to calculate heat transfer. And the last example is about the electrically heated or actually the cooling of a windshield or the heating of a wind screen. The electrically heated 0.6 meter high, 1.8 meter line windshield. Dimension and it is windshield. Of a car is subjected to parallel wind at 1 atmosphere, 0 degrees Celsius, and 8 kilometers per second. These are information about the fluid, which is air here. These are information for the surface. The electric power consumption is observed to be 50 watts when the exposed surface temperature of the windshield is 4 degrees Celsius. So if temperature of the surface Ts is 4 degrees Celsius, this much of power is required to heat or temperature to have a steady operating condition. No change in the temperature. Disregarding radiation and heat transfer from the inner surface and using the momentum heat transfer analogy, determine the drag force the wind exerts on the windshield. Okay, this time we have information about the heat power. We are interested to calculate drag force. Very interesting example. The windshield is like this. This is the property of the air, 0 degrees Celsius, 80 kilometers per hour, the velocity, the dimension of the windshield, and the properties for the air. First of all, always we need to go to the table A15, find the properties, because here it is mentioned that pressure is 1 atmosphere. Table A15 is information of the related to properties of the air at this pressure. Find the temperature, 0 degrees Celsius, 0 degrees Celsius, then these are properties. All of them simply you can find for the air at the pressure. Okay, so these properties, rho, Cp, and Prandtl. How about the information which we need? If you remember this equation also in previous example, the drag force can be calculated by this equation. If F is equal to Cf As rho V power 2 divided by 2. Okay, let's see what we have, what we don't have. We, or the velocity of the air we have, it is by in terms of kilometer per hour, we need to convert to meter per second. About the density we have here from the table, AS, we can calculate that, the surface area. How about CF? Do we have that? No, we don't have CF. But we have equation which we can use that to calculate CF. Like the CF is 2h Prandtl number power to third divided by rho v Cp. Again here, let's see what we have, what we don't have. We have rho, we have v, we have Cp as well, Prandtl number as well from the table. How about the h? Do we have that? No, we don't have h. So how we can find h? We have this equation, if you remember, for convection heat transfer. If we restructure that, the h can be calculated by this equation. But do we have the information to calculate h by this equation? Let's see. T infinity, 0 degrees Celsius given. Ts, 40 degrees Celsius. We have AS, the dimensions are given. So we can calculate that. How about Q dot? Q dot is the power, here because we have a steady operating condition means these 40 degrees Celsius remain constant, these 0 degrees Celsius remain constant. But we have heat transfer. When we have heat transfer in this problem, but temperature remain constant, it means all of the power which is being used here, that 50 watt, will be transferred by heat transfer to the air. So we have a steady heat transfer actually. So the Q dot here will be 50 watt. This is the point and note which you need to know in this example. So by this uh, equation and this information, we can calculate H. So we have H as well here again. When we have calculated H by this equation, we can substitute here to calculate CF. When we have calculated CF, we can substitute in this equation because we just need to have CF to calculate the drag force. So this is drag force, the answer for this question. Here are only review for what you have learned in the chapter. Okay, by this we reach end of this chapter.